Hi everyone, welcome back. The learning goal for this video is for you to be able to predict the three-dimensional structure of a molecule and classify it as polar or nonpolar overall. So here's an example of methane, CH4. The central atom carbon is bonded to 4 hydrogen atoms. And if you were to draw the Lewis structure, it may look something like this. This is two-dimensional. But molecules exist in three-dimensional shapes. And so this two-dimensional Lewis structure is a little misleading because it appears as though the bond angle here between this hydrogen, carbon, hydrogen is 90 degrees. But what we'll learn in this video is that molecules will take the most stable form, three-dimensional shape, in order to minimize repulsion. And so actually the bond angles for methane are 109 degrees, which is larger than the 90 degrees. And we can show this through this ball and stick model. And if we're drawing it on paper, you can actually show this type of geometry using bold and dashed lines so that this hydrogen, for example, is coming at you and this hydrogen is going into the paper to illustrate this molecule in its true tetrahedral three-dimensional form. So let's discuss more about why that's the case. Is the bond angle 109? Well, it's all based on valence shell electron pair repulsion theory, which I will refer to as VSEPR theory. And it describes the orientation of electron groups around the central atom. So your central atom is going to be your focal point when you're determining molecular geometry. And we're always going to be counting the number of electron groups to determine the molecular geometry. Basically, VSEPR theory states that electron groups are arranged as far apart as possible around the central atom. The overarching theme of chemistry is that opposites are attracted to each other, like charges, for example, like these electron groups don't like each other, they repel. And VSEPR theory states that the specific shape of a molecule is determined by the number of atoms attached to the central atom. And so this will be a core chemistry skill that you're developing, is predicting the shape of molecules. So let's start with the simplest, 2 electron groups. So when we talk about electron groups, we first want to focus on the central atom, and it's how many things are attached to it. So for example, carbon dioxide has 2 electron groups. It doesn't matter that it's a double bond. You just treat this as 1 electron group. Okay, so find your central atom and count how many things are attached to it. So in the molecule of carbon dioxide, 2 electron groups are placed around the central atom. And the repulsion of those electron groups, they want to get as far apart as possible. The repulsion is minimized by placing the 2 groups on the opposite sides. This gives what we call a linear shape and a bond angle of 180 degrees. So that's the largest bond angle it can form to get those 2 groups as far apart from each other as possible. So the shape with 2 electron groups around a central atom is called linear. What about if we have 3 electron groups? So let's look at the example of formaldehyde. So this is the Lewis structure for formaldehyde. Find your central atom and count how many things are attached to it. So this has 1, 2, 3 things attached to it, so 3 electron groups. And those groups want to spread out as far as possible. Right now, the Lewis structure looks like a 90-degree bond angle and 180, but they want to spread out even more. And so that is done by achieving a bond angle of 120 degrees for each of them. So there's a 120 bond angle here, here, and here. And this shape we call trigonal planar. So if you have a molecule that has 3 electron groups around the central atom, then this is trigonal planar. Now, what happens though if you have a lone pair? So let's look at lone pair. So sulfur dioxide, this is its Lewis structure, but technically it's actually not a linear molecule, even though it might seem that way as it's drawn. So when we count the number of electron groups around sulfur, that central atom, we include lone pairs. So a lone pair is considered an electron group. So we have 1, 2, 3 electron groups. And so this looks like it is trigonal planar, and we call that the electron group geometry, where it does have 3 electron groups. But because one of the electron groups is a lone pair, the molecular geometry, what we see, because we don't see the lone pair, but it does play a role in the shape. But what we see is what's called a bent shape. So the shape with 2 bonds, 2 bonded groups, and 1 lone pair on the central atom is bent, and the bond angle is still 120 degrees. Let's look at the scenario where there are 4 electron groups. So let's come back to methane. Methane has 4 electron groups, or carbon has 4 electron groups attached. And we saw in the earlier example that the repulsion is minimized if those 4 electron groups are arranged in a shape that maximizes that bond angle to 109 degrees Celsius. This is called tetrahedral. So the shape with 4 bonded atoms on the central atom is tetrahedral. The bond angle is 109 degrees. And you can show that by drawing 2 lines in the plane of your paper, 1 bold and 1 dashed, to illustrate it on 3D. Now, ammonia has 4 electron groups too, because remember we count the lone pair. So 1, 2, 3, 4. And so its electron group geometry is still tetrahedral. They still have to spread out as much as possible. But if we're asked for the molecular geometry, we only see the bonded atoms. So what we're left with is what looks like a trigonal shape, but actually a pyramid, right? And so it's not flat, it's not trigonal planar, but rather it's trigonal pyramidal. And once again, you can actually illustrate that in 3D. Trigonal pyramidal has 1 in the plane, 1 bold, 1 dashed. And usually for drawing in 3D, I include that lone pair, but it doesn't have to be on a line or anything. It's just on the nitrogen atom. Now, in case of molecule of water, in the case of water, we have oxygen. It has 4 electron groups in the Lewis structure attached to oxygen, but 2 of them are lone pairs. So the electron group geometry is still 4 electron groups tetrahedral, but the molecular geometry, if we remove those lone pairs, we're left with something that looks bent. And you could draw this bold and dashed, or a lot of times with water, we just draw it this way where it's in the plane and we assume the 3-dimensional nature of that molecule. But the bond angle is closer to 109 for this bent molecular geometry as opposed to the 120 degree bond angle that we saw in a previous example. So the bond angle is based on the electron pair or the electron group geometry. So here's a nice summary table going through all the different electron group geometries and the bond angles for those electron group geometries and the molecular shape. And then they give you examples of those different types of molecules associated with each category. And so when you're doing your homework problems, I highly recommend having this accessible so that you can use it as a tool. So let's go through the guidelines for predicting molecular shape. Now, first and foremost, you have to be able to draw the Lewis structure correctly. So that I went over in a previous video. Make sure you go through that in great detail first, practice some problems before tackling this video here on molecular shape. Step 2, you're going to arrange the electron groups around the central atom to minimize repulsion. And then you're going to use the atoms bonded to the central atom to determine the shape. So let's do an example together. We have dihydrogen sulfide here, H2S. And first we have to draw the Lewis structure. We have to count the number of valence electrons. So hydrogen each gives us 1, sulfur gives us 6. So we have 2 times 1 plus 6 is equal to 8 valence electrons. Now, sulfur has to be a central atom. Hydrogen needs to always be on the outside because it can only form 1 bond. I've already connected the skeleton together. And then I have 1, 2, 3, 4. Any leftover valence electrons go on the outside atoms, but that's not the case here because hydrogen cannot have more than 2 electrons. So the leftover electrons, the 4, go now on the central atom. And then we check to see if the central atom has an octet, and it does. So no need for a double or triple bond. Once again, hydrogen can't make double or triple bonds, so we're good to go here. So this is the Lewis structure. The next thing you're going to want to do is to determine the number of electron groups attached to the sulfur here, the central atom. So it's 1, 2, 3, 4. So we have 4 electron groups, which implies that we have tetrahedral electron group geometry. But because we have 2 lone pairs, the molecular geometry is bent. And the bond angle, because it's tetrahedral electron group geometry, is about 109 degrees. So if we wanted to use the table, we can go 4 electron groups with 2 bonded atoms and 2 lone pairs. So this is this one here, and that would give us bent geometry. So this is how you can use that table confidently, especially as you're practicing your problem sets and different types of questions. This table will be very useful in helping you predict molecular geometry. All right, pause the video and try this one on your own first, and then check your work with me when you're done. All right, so basically we just need to figure out the geometry, but before we do that, we'll need to draw the Lewis structures. So for phosphorus trifluoride, the Lewis structure you should have derived looks like this. And please, by all means, check your work with me. And then if it's not lining up, then email me with questions and we can work on deriving Lewis structures during a one-on-one session together. But for right now, hopefully you derive phosphorus trifluoride. It looks like this. And then focusing on the geometry, we count the number of electron groups attached to phosphorus. We have 4 electron groups. So that's tetrahedral electron group geometry, but we have 1 lone pair. And so if we go back to my apologies there, let's go back to here. 4 electron groups, but 1 lone pair. That's trigonal pyramidal. Bond angle is about 109. All right, let's do water. So water is Lewis structure looks like this. It also has 4 electron groups, but 2 lone pairs. And so its molecular geometry is bent, but the bond angle is still about 109. And carbon tetrachloride, its Lewis structure looks like this. Make sure you're always including all the lone pairs. That central atom carbon has 4 electron groups, 0 lone pairs, and so therefore its molecular geometry is tetrahedral, and the bond angle is 109. So just to review again from that table, in that example we just worked, we saw 4 electron groups with 0 lone pairs is tetrahedral. 4 electron groups with 1 lone pair is trigonal pyramidal. 4 electron groups with 2 lone pairs is bent. All right, so once you feel confident in deriving the shape, then we can start thinking about, well, what's the polarity of the molecule itself? In a previous video, we discussed polarity for a single bond, but now we want to be able to determine the polarity for molecules overall. So nonpolar molecules such as hydrogen, chlorine, and oxygen are nonpolar because they contain nonpolar bonds. So regardless of what their geometry is, they're just nonpolar overall. But there are molecules that contain polar bonds, but their dipoles cancel out because there's symmetry. So if there's symmetry there, there are cases where a molecule contains polar covalent bonds. So for example, carbon oxygen is polar covalent. Notice the dipole arrows. But because of the symmetry, those dipole arrows cancel each other out. And because they cancel each other out, it's considered a nonpolar molecule overall. Carbon tetrachloride, same thing. These individual bonds are considered polar covalent, but because they're in this symmetrical tetrahedral geometry, they cancel out, and therefore this molecule is considered nonpolar overall. Polar molecules such as hydrogen chloride are polar because one of the molecule is more negatively charged than the other. Remember in the previous video, I said, in this case here, this chlorine doesn't like to play, right? It's, taking all the electrons away from that hydrogen, right? It's not sharing nicely. The polar bonds in the molecule are not canceling each other out. So there's nothing else going in the other direction. No other dipole arrow is canceling this one out. And so therefore these electrons are shared unequally in this polar covalent bond. And so we would say, this molecule overall, hydrogen chloride, is polar. And this is going to be a core chemistry skill in identifying polarity of molecules. So we'll continue to work on this. Let's look at another example you're familiar with. Let's look at water. So water, we just learned, has bent molecular geometry. So if we draw the structure, it looks bent like this. And the individual bonds, OHs, are polar covalent. But because it's not a linear molecule, notice how the arrows are pointing towards the more electronegative atom, but they're not lined up. They don't cancel each other out like they did in carbon dioxide. And so therefore, since the dipoles do not cancel, water overall is considered a polar molecule. And you can see that here, like those yellow arrows are not canceling out. And so therefore, this molecule overall is polar. And that's all because the shape itself is not a symmetrical shape. It's bent and not linear. Let's look at ammonia. So ammonia has trigonal pyramidal molecular geometry. Nitrogen hydrogen is a polar covalent bond based on the electronegativity difference. And if we point the arrows, they're pointing towards nitrogen. Notice how they don't cancel each other out. And so because the dipoles do not cancel out, this molecule, ammonia, is polar overall. So here's a guide to determine the polarity of a molecule. First, you'll want to utilize your knowledge from a previous video and determine if the bonds are polar covalent or non-polar covalent. And then if the bonds are polar covalent, draw the Lewis structure and determine if there's symmetry. If it's a symmetrical molecule and the dipoles cancel out, then it's non-polar overall. If it's an asymmetrical molecule and the dipoles do not cancel out, then it is a polar molecule overall. Let's do an example together. So let's determine the molecule oxygen difluoride, if it is polar or non-polar. So the first step we got to do is determine its Lewis structure. So oxygen gives us 6 valence electrons, fluorine gives us 7. So we have 20 valence electrons total. Fluorine is more electronegative than oxygen. So oxygen's the central atom, and we connect those together to make the skeleton. And then we have to complete the outside atoms octet first. I've drawn 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I put the leftovers on the central atom now, 17, 18, 19, 20. I check to see if oxygen has an octet. 1, 2, 3, 4, 5, 6, 7, 8, and it does. So this is the Lewis structure for oxygen difluoride. Now let's then determine if oxygen fluorine is a polar covalent bond. So oxygen has an electronegativity value of 3.5, fluorine is 4.0. 4.0 minus 3.5 is 0.5 electronegativity difference. So this is those are polar covalent bonds. But now we have to determine if there's symmetry here based on molecular geometry. So oxygen has how many electron groups attached to it? It has 1, 2, 3, 4 electron groups. How many lone pairs? 2 lone pairs. So 4 electron groups, 2 lone pairs. What is the molecular geometry? It is bent. So if I draw this structure again, kind of really emphasizing that bent geometry. And then I draw my dipole arrows pointing towards the more electronegative atoms. Do those arrows cancel out? No. So the molecule overall is polar. All right, go ahead, pause the video, try the study check on your own, and then check your work with me when you're done. All right, so phosphorus bromide, I'm going to go ahead and just draw the Lewis structure here. Once again, check your work with me. If you're not getting the same Lewis structures, please email me and schedule an appointment, a one-on-one session, and we can go through drawing the Lewis structures together. I'm happy to help. So in this case here, we want to check first of all, if phosphorus and bromine even have polar covalent bonds. So phosphorus electronegativity value, which you can look up because I'll provide those values for you on any in-person assessment. Bromine is 2.8. 2.8 minus 2.1 is 0.7. So yes, the bonds themselves are polar covalent. with bromine being the more electronegative atom. So now let's determine molecular geometry. Phosphorus has 1, 2, 3, 4 electron groups and 1 lone pair attached. So what is the molecular geometry? Good. Trigonal, pyramidal. And because it's trigonal pyramidal, I can go ahead and draw this kind of mimicking what we saw earlier. There's 1 bold, 1 dashed. And what I mean by mimicking earlier, let's go back and look at that table. As you can see here, this is trigonal pyramidal, and you can see one's in the plane, one's coming at you, and one's going into the paper. And you can see that here as well, kind of mimicking the bold and dashed lines there. And so if we draw the dipole arrows pointing towards the more electronegative atoms, do they look like they cancel out? No. So overall, is this molecule polar or nonpolar? It's definitely polar. Good. What about HBr? So let's go ahead and draw HBr. The electronegativity values are 2.1 for hydrogen and 2.8 for bromine. So we have an electronegativity difference of 0.7. So definitely polar here as well. Polar covalent bonds. And if we draw a dipole arrow, this is technically a linear molecule here, right? But because one of the atoms is significantly more electronegative than the other, then overall this molecule is polar. Methane, CH4, we've already determined to be tetrahedral in geometry, but let's look at the carbon-hydrogen bond just to see if it's even polar covalent. So carbon's electronegativity value is 2.5 and hydrogen is 2.1. That's an electronegativity difference of 0.4. And we said anything between 0 and 0.4 is considered non-polar covalent. And so therefore, regardless of whatever this structure looks like or what it's, so whatever it looks like here in terms of geometry, if it's composed of all non-polar covalent bonds, then this molecule overall is non-polar, regardless of geometry. So because it only has non-polar covalent bonds, the molecule itself is polar overall. Or non-polar overall, my mistake there. So the molecule itself is non-polar overall. All right, thank you for watching, and as always, email me with any questions.